Today we're talking about the fundamental counting principle. What does the word fundamental mean to you?
Basic.
Basic. Okay. So when we hear the word fundamental a lot and crucial. Okay. When we hear the word fundamental, a lot of times we hear it in a sporting event setting. So in a basketball game, we might talk about our fundamentals are going back to basics. So if you can't dribble, if you can't do a layup, if you can't make a free throw, these are basics. Like we have to do those. They're basic skills and they're really important. Like you can't play the game of basketball if you can't do those things, right? So when we use the word fundamental in math, in pretty much every area of math, we have something that's called the fundamental blank, 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 okay? So right now we're talking about our fundamental counting principle. When we use that word fundamental, it means this is a basic idea to it and really important, like everything builds from this idea, okay? Our fundamental counting principle talks about the number of ways that things can happen. So it says, if we have two events, okay, when we use the word event in probability, we don't mean like a party, okay? An event is like drawing a card, or rolling a die, or picking out a shirt. Okay, these are events, okay? So it says if we have two events, and one event can occur m ways. There's some number of things that can happen there. And there's a second event, and that one can occur n ways. Then the number of ways that those things can both happen is m times n. A little bit confusing here. So let's think about a more solid example. Let's say that I look at my clothes and I have 5 shirts. You can call them A, B, C, D, E. And I have 3 pairs of pants, 1, 2, 3, and everything matches. Okay. How many different ways could I put together these shirts and pants to make outfits? Okay. So I could do A shirt with 1 pants, or A shirt with 2 pants, or A shirt with 3 pants. Or I could do B shirt with 1, B shirt with 2, B shirt with 3. Or I could wear C with any of them, D with any of them, E with any of them, and it starts to look like a lot of chicken scratch, but if we counted up how many connections there are 15 connections. Okay? The fundamental counting principle says I can multiply the number of options I have for the first thing times the number of options I have for the second thing, and that would tell me how many total options I have. Okay? So there's 15 different outfits there, which I own a lot more than 5 shirts and 3 pants, and sadly still feel like I have nothing to wear, right? That's always the dilemma of a girl, as we feel like we have nothing to wear. But that's already 15 things, and that's hardly any clothes at all, right? These can get very large very quickly. Okay, as we multiply numbers together, they can get very large very quickly. The fundamental counting principle extends for any number of events. So if I'm not only picking a shirt and pants, but I'm also picking socks and shoes, okay, we can multiply each number of individual ways together, and that will give us our total number of ways. And that's what the fundamental counting principle says. So our first example says police use photographs of various facial features to help witnesses identify suspects. One basic identification kit contains 195 hairlines, 99 eyes and eyebrows, 89 noses, 105 mouths, and 74 chins and cheeks. And that's one thing together. It's like one template for chins and cheeks together. It's not chins and then cheeks. Okay. What I imagine here is kind of like, I had some flip books with faces when I was little, but my daughter has one that I forgot to bring in that's like Disney princesses, and only part of the page turns, and like the pages are cut. So like I can put Jasmine's head and Belle's body and Snow White's skirt or something, you know, and you can fit together different pieces. So then how many different princesses could we make? Okay, and that's the kind of thing here where we can select all these different hairlines. We pick one of those. We can select one set of eyes. We can select one nose. How many different faces can we make when we put this all together? So part A says the developer claims that it can make billions of faces. Is that really true, or are they just using billion as a word for a lot? Because we do that. We just say, you know, billion and just throw it out there and we just mean a lot. Do they really mean billions, or do they just mean a lot? So to find out how many different faces we can make, our fundamental counting principle says each of those things is an event. Picking a hairline is an event. Picking eyes is an event. and we can multiply the number of ways that each of those events can happen. So I can do 195 times 99 times 89 times 105 times 74. Calculators are going to be really important when we're working on probability problems. So don't want to do this in your head. Multiply it all together.
Didn't even do it.
And I end up with, on my calculator, it says 1.3 and then there's a lot more stuff. And then that seems like kind of a weird answer, right? Because I'm multiplying big things and I'm only getting 1 point something. That doesn't make sense, right? But at the end of this number, there's an E10. What does that mean? Scientific notation with a times 10 to the 10. So this means 1.3 times 10 to the 10th power. Or is it 10 or is it 18? 10. It is 10. Okay. So what that means is I'm going to go 1, 3, move my decimal 10 places. So I moved it once, 2, 3, 4, 5, 6, 7, 8, 9 places.
1, 9.
It's 10.
1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So I move it once for the 3, and then 9 more times. So I get 9 zeros there.
So it's not billions, it's billions.
So it's more than a billion.
I got a 0.
But less.
Yeah, I got it.
I did forget a 0.
Oh, that would change things.
Just a little bit.
I said 9 zeros, but I only wrote 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Now I actually have 9 zeros. Okay. So now 13 billion different faces.
That's billions, plural.
That is billions, right? There are really more than 13 billion because there were more numbers here that I just turned into zeros, but they were really numbers. So there are more than 13 billion different faces, which could make a really overwhelming thing for a witness who maybe doesn't remember what happened very clearly. Having to think about 13 billion different possibilities would be a little overwhelming. So part B says, a witness can clearly remember the hairline and the eyes and eyebrows. So how many different faces could they still put together with the other information? So witness testimony is a really interesting thing in psychology, actually, because it's very flawed, especially in a stressful event. And so witnesses often don't remember things exactly the way they were. But this witness is like, I know for a fact the guy was bald because the sun was reflecting, right? I got that. I'm positive of that. And I know for a fact he had a unibrow, because how could you forget that, right? So this witness knows 2 things, for sure. And the rest of it, they didn't really get a good look at because they were distracted by the sun reflecting in the unibrow. So how many faces can they still put together? So we'd have 89 noses to still choose from, 105 mouths to still choose from, and 74 chins and cheeks to still choose from. So we multiply just those parts together. And it's 691,530 faces to look at. So not nearly as many as before, but that's still a whole lot of possibilities to consider. So hopefully they can kind of narrow that down a little bit.
So were you following the problem on there? Said you also did that.
I did the, no, they know the eyes.
Okay.
Eyes and eyebrows are one characteristic together.
Oh.
Yeah, so we just need the noses, the mouths, and the chins and cheeks.
For A, would you just leave the answer as 13 billion, or would you write, oh, yes.
You could, for the answer for part A, you could do the scientific notation or the full notation. Either one's fine.
Could you do the one with the E?
No, E isn't really proper math notation. It's just a calculator symbol. All right. We're going up to our next example. The next example says, at a restaurant, you have a choice of 8 different entrees, 2 different salads, 12 drinks, 6 desserts. You're gonna put together a dinner that's gonna have one of each of those things. So how many different dinners could you end up making? So I am a horrible decision maker. Not like big life decisions, like I can handle that, but like what to eat is like I can't do it. I cannot decide what to eat. Like I cannot make minor decisions. So going to new restaurants is a very overwhelming thing for me. I like trying new things, but I look at the menu and I'm just like, too many choices to make. And then you finally think you made your choice, and then the waitress is like, and do you want a soup or a salad? I want a salad. Okay, do you want a Caesar or do you want a house? A house. Do you want Italian, Thousand Island, French, or ranch? I'm like, I thought I was done making decisions, right? So this doesn't even seem like that big of a menu. 8 entrees, that's not that big of a menu. Only 2 salads, 12 drinks, they have a lot of different soda, I guess, and 6 desserts. That's a good dessert menu, so I'd probably like this place. Right? So this isn't even that huge of a menu, but when we try to figure out how many meals, we're going to multiply each of those numbers. So 8 entrees, 2 salads, 12 drinks, 6 desserts. And our fundamental counting principle says we can multiply each of those individual options together, and that will give us our total number of options, which is 1,152 different meals that we can make at this restaurant. Which means, if I went to this restaurant every single day, I could go there for more than 3 years and have a different meal every dinner.
Well, I mean,
Okay.
the drink could be different.
Right. So, I mean, you would just change one thing each day. So I could just have, a different drink. It would take me 12 days to go through the options there. So,
You'd have to be rich to eat
So
there every day for
that's-
3 years, though.
well, maybe it's just
Pretty wild.
a fast food. But still, yeah, it adds up, right? So that's a lot of decisions.
Are you eating 3 meals there a day? Or
Oh no, I'm just saying dinner because it just said didn't say dinner somewhere in there. How many different dinners?
Oh.
Yeah. So I was just thinking dinner. We start going there 3 times a day. We just do it in a year. Although I would think their breakfast and dinner menu would probably be different.
Well, maybe. Maybe they don't have a breakfast menu.
All right, the next one says the standard configuration for a New York license plate is 3 digits followed by 3 letters. How many different license plates are possible if the digits and letters can be repeated? So that means there's a possibility that you have a license plate of 111AAA. Okay? I would like that. It's easy to remember. What I do in these problems is I draw myself some blanks. We have 3 blanks for digits, 3 blanks for letters. How many digits are there? Be careful.
9. 10.
10, because 0 is a digit.
Oh, yeah.
So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 different digits. So any of those 10 digits could go in that first blank. And since we are allowed to repeat, any of the digits could go in the second blank, and any of the digits could go in the third blank. How many different letters are there?
26.
26 letters in our alphabet. And since we can repeat, I could use the same one over and over.
What would we do if we weren't allowed to repeat?
We'll do that in part B.
She's ahead of you.
It just doesn't do the thing, does it?
Mine's a big calculator. I think it does it eventually, but it takes a while.
So I get 17,576,000 different license plates that are possible then. Okay, that's a good thing for the state of New York. They have a lot of vehicles. Part B asks, what happens if we can't repeat? So we're not allowed to do 111AAA. We have to do like 1, 2, 3 ABC. Okay? So how many digits could go in the first blank?
10.
Anything. But now that I've used up a digit, how many can go in the second blank? 9, 8. Letters, any letter can start it out, but once I've used up a letter, I can't use it again, so we have to count down. And we get
A lot.
still 11,232,000, but that is 6.3 million fewer license plates. So that's a small alteration to make, and it actually cut out a whole lot of options. Questions? Last example. How many different 7-digit phone numbers are possible? 2, 3, 4, 5, 6, 7. So we got 7 things to pick here. 7 digits phone number. If the first digit cannot be 0 or 1, because if it's 0, we're calling the operator. If it's 1, it's queuing our phone that we're going to do a long distance number. So we can't start with 0 or 1. So how many things can we start with? 8. How many could be the second number?
10.
Anything's fine because it didn't tell us to restrict our second number. It just told us to restrict our first number. What about the third digit? 10, because we're allowed to reuse numbers in a phone number. So all the rest of them are 10. And I don't actually need my calculator for that one. You get 8 million different possible phone numbers. Now this isn't totally true because this would allow for 911 to be the first 3 digits, which would be a problem. Okay, so if we try to take that restriction out, it's difficult to do it, but that would cut this number down quite a bit. Okay, take all the ones out that ended up with 911 at the beginning of it. Also, phone numbers can't begin with 555. 555 is reserved for fake numbers. So when they make movies or TV shows and somebody gives out a number, it's supposed to be a 555 number. They don't always do that. In the movie Bruce Almighty, several years back, Bruce played a character who was kind of like a god character, and he had a pager so people could page their requests to God, and his pager number was not a 555 number, and it belonged to a little old lady in Florida who is living a wonderful retirement now after suing the company. Because her phone did not stop ringing for people wanting to contact God with their request. So she sued the filmmakers and ended up with quite a large amount of money from that. A student in the other hour told me that he heard in a different area code, because this could happen in any area code, then he heard that in a different area code it was actually a pastor who had that number, so then when people would call and ask for God, he would share with them the gospel, and I'm like, that is awesome. So that's really cool. So that problem isn't totally realistic in terms of how many phone numbers are actually possible. Your homework comes from what says section 12.1 there, but it's not 12.1 of our textbook. It's out of that handout packet that I gave you. Treat that handout packet kind of like your textbook for the next about week and a half. Don't do your homework on there because then you would need to hand it in and you won't have it to do your homework for the next lesson. So just kind of treat it like your textbook. 12.1 is that front page and then do the selected problems there.
We write on it.
You can write on it, but don't write your answers on it and plan on handing it in, but you may write on it.